All right, we got the recording going here. We're starting week 2 of geometry. Got quite a few people online. Nicole here in the classroom. And today is going to sound an awful lot like stuff that you learned in algebra, because we're going to start talking about slope, and then that will transition into things involving something called transversals. Anybody ever heard that term, transversal? Well, that's another one of these definitions that you'll see in this unit. So it's another packet, another handout that normally, if we were all together, I would print out for you. Does anybody want the hard copy? Okay. All right. So I will. If you do, let me know. We'll figure out how to get it to you. I got one request here in the classroom for that, so I'll send that to the printer real quick. All right, and Rashad also. Okay. Do you have a way to get up here at all, Rashad?
Not really, because my sister be so busy, so I don't be able to come to school like that.
Even just to stop in and pick something up?
Last time I came up there to pick something up was last year.
Okay. Well, if you can figure that out, I'll have a copy available for you. Okay, just let me know.
Okay.
I mean, I don't know who's got a printer and who doesn't. It's not fair for you guys to have to print these out at home. Anyway, using up your ink. Ink is expensive. So
I can print it at home. I got a printer.
Oh, do you? Okay. Well, that's obviously another option.
Okay.
So right off the bat here, with this slope review, you see 4 different lines. Up to the right, up to the left, a flat horizontal line, and a vertical line. You guys remember how slope works for those? And from algebra, there's only 4 different types of slope, and that's what those 4 graphics at the top there are about. Anybody remember any of them? Well, this first one is positive.
Slope.
Second one is negative. The third one, the horizontal one, is 0 because it's a flat line. If you guys remember the term rise over run, that's how we come up with the slope. So a horizontal line has 0 rise, but the run, the left and right movement, like a number line, is infinite. This fourth one, the vertical one, is the opposite. Obviously, it's going to be perpendicular to the horizontal line, but it is what's called undefined. There we go. Undefined. And these are like absolutes because they always are going to be that way. The line goes, if you were in my algebra class, you'd see me standing in front of the board with my hand up in the air to the right for positive, my right arm, my left arm up for negative. Because really, I don't care about where the lines are going, down in this area. I'm only, the direction that's going up and out of the graph is what I key in on. That's going to tell me whether it's positive or negative. And right below that, you can see this little equation here, M equals rise over run.
You have to take it down a little bit.
Oh, you can't quite see it? Okay. Is that better?
A lot more. That's good.
Okay. So this first one here on the left says, given a graph, use M equals rise over run. Anytime you see M in any of these equations, we are talking about slope. Rise over run is used when we have a graph. Trying to make this a little bigger. Because you got a point here at A and another point B. Anytime I got a graph, it's going to be easier to count the squares. Now, we're not talking about the distance between A and B. We're talking about how far I have to go up to get to the level where B is, and then how far over I have to go to actually get to B. That's the rise and the run. Rise here is up 1, 2, 3, 4. Run is 5 to the right. 1, 2, 3, 4, 5. All I'm doing is counting squares. The examples to the right, however, now I got to actually do the calculations. If all I have are the points, find the slope of line AB. Well, it might still be the same line. It might not be. You've got some options. You can graph it and do the rise over run counting, or you can just do the calculations. So in some ways, this you might look at this as being similar to using the distance formula, because we're using X and Y values from two different points. Our outcome is going to be a little bit different. We're not looking for the distance or a measurement between 2 points. We want to know about how steep the line is. The higher the number, the steeper the line is. The lower the number, the closer it is to 0, the flatter the line is. If you've worked construction, you know about rise and run. Anybody that's built houses, anybody that's built stairs, I just finished building some stairs to our deck. I had to use rise and run for that. It's how much up for the rise, how much over. You look at a roof of a house. Around here, they're steep, pretty steep. Go to someplace like, say, Norway or Finland. Those houses over there, they're really, really, really steep. Well, why do we need a steep slope roof around here or in some place like Finland?
Snow accumulation.
Yes, exactly. Snow accumulation. If snow is heavy, it's basically water. A gallon of water equals 6 pounds. So you want a roof that's sloped enough so the snow can slide off or melt and go, not accumulate on the roof. If you've ever seen on the news when there's been a blizzard, people are up, like in upstate New York, around Buffalo. You see it a lot over in Buffalo. People are up on their roof shoveling off the roofs of their homes, because what happens with all that weight, you could potentially have a roof collapse. So the structure that's under the roof, that's all built according to rise and run. And that gives you the slope. So if you're in construction and you've got to order trusses to put on the top of your joists to build the roof, that's what you're going to be hearing about. You're going to have to know those measurements. If you go out and if you live in the desert, your roof is basically going to be flat because you don't have to worry about snow. Now, they still get some rain in places like New Mexico or Arizona. So it's not perfectly flat. You still have to have a little bit of slope for the water to run off. But you'd be surprised how little slope you need. I used to work in the water and sewer industry and did a lot of real estate development in my previous career, my previous life. For water to flow, you only need a slope of 1 inch per 100 feet. So if you got a pipe from one end to the other, if all you're talking about is just water flowing, it only has to drop 1 inch over that 100 feet. That's not very much slope at all. That's 0.01. But it's enough for water to flow because it has water flows very easily. If you've ever had to, if you've ever had an area around your house where water ponds and you're trying to figure out a way to get rid of it, just dig yourself a little trench. You don't have to have a huge ditch. You know, you can figure out a way to get the water away from your property because it doesn't require a lot of slope, pretty much flat. So these two formulas here, now you're going to see these come up a lot in this second unit. Questions about any of that so far? All right, so what would the rise and run, what would the slope be on this problem number 2 here? Can everybody see that? From P to Q. The first thing I try to identify before I even do any calculation or any counting, does that line in number 2 have a positive or negative slope?
Negative.
It's negative, correct. It's a negative slope. That's, I tell my algebra students all the time, the biggest source of mistakes is forgetting the minus sign. And it's absolutely true on these kind of slope problems.
It'd be 3, -6.
Okay, you got a rise of 3. Let's see on this level, 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay, can you reduce that, Jonathan? 3 over 6?
Be 1/3, 1 and 3.
Not quite. 3 over 6. Divide them both by 3. You got the top right.
Oh, it'd be a half.
Yeah, 1/2. Negative 1/2. Right. And that, what I just asked him about is another good thing I want to emphasize with this slope stuff. Slope comes out as a fraction. You don't want to put it in a calculator. You don't want to make it into a decimal. That doesn't help you. We need both numbers. We need the rise and the run. Even if it's 7 over 5, I don't care what it is, just leave it as a fraction. And sometimes, as with any fraction, it'll come out where both terms are divisible by some common number. Just like this one, 3 over 6, both of those are divisible by 3. So you want to reduce your fractions to lowest terms. Because really, if you look at this line, I'm going up 1 over 2, and I'm back on the line. Up 1 over 2, I'm back on the line again. Up 1, left 2, I'm back on the line. And that's the key about slope. If you don't remember that from algebra, the slope goes from one point to another point on the line, and it has to be repeatable. You have to be able to do that same motion over and over and over again and get back on the line. Now, 3 and 4 might be a little bit of a puzzle, but they are examples of the other 2 types of slope. Look at 1 and 2. We got a positive, we got a negative. People get 3 and 4 mixed up all the time. One of them is slope of 0. The other is a slope that is undefined.
3 is undefined.
3 is undefined. That's right. Because it has infinite rise, but 0 run. Four has the opposite, infinite run, but 0 rise. Let me see if I can show you that in another way. All right, so if I've got I've got a vertical line and the term I've been using is spelled like this, undefined. Don't confuse that with the term infinite. This line has infinite rise. But zero run. Okay, so if I make that into an actual calculation, have you ever seen that symbol? This one on the top here.
Is it infinite?
That is infinite, right? That is the symbol for infinite or for infinity. And the reason that it's undefined is because we can't divide by zero. No mathematician ever has been able to satisfactorily define how you can divide anything by zero. Because division by its nature is you're dividing by something. Well, zero is nothing. So how can you divide by nothing? I don't care what the number is. And if you picked 2 points on this line and you figured out the run, well, the run is going to be zero because they're at the same point on the x-axis. Remember, this is your x-axis. This is the y-axis. If both of these are at 3, you got 3 minus 3 on x. Okay, the opposite of that is your horizontal line. Because now horizontal line with zero slope, it's exactly the opposite of that other fraction. We have no rise, but infinite run. Now, we can try to divide zero by any number that we want to. We're still going to get zero. So those are two kind of unique situations that you got to get comfortable seeing and working with. Questions on either of those so far? So that may remind you of your earlier time in algebra. So what I'd like to do is take a minute and everybody work on problem number 8. And in order to do problem number 8, you're going to have to use that y2 minus y1. It's right at the top of, whoops, you can go to the other one. It's this formula right here. It's this calculation. And all it is you take the y value from each point, subtract 1 from the other, then you divide it by the x values. Do the same subtraction on the top, on the bottom. And for problem number 8, whoops, too far. I'll go ahead and pause things. You guys can have a chance here to do a quick calculation. So on that particular problem here, we got 2 points. One of them is -7, -3. The other point is 0, -3. If you remember from your ordered pair graphing, the first term is always X, the second term is always Y. Now I don't really care which one you say is the first. And if you look at this equation here, all this does is give you an X and a Y from two different points. That's what the 1 and the 2 refers to. This is not an exponent situation. This is just the X and the Y from point number 1. This is the X and the Y from point number 2. So when you make the comparison, when you make the comparisons here, what you're doing is you're filling in this box here for this point, and you're filling in this box for that value for Y, and the minus sign in between stays. So this is the one I'm going to say is point number 1, and this is the one I'm going to say is point number 2. And the only reason I do that is because that's the way I wrote it down on my paper. You could do it any way you want. It won't make any difference in your calculations, and I'll show you what I mean. So the Y values, point number 2 is -3. My formula involves subtraction, and I'm subtracting -3 from that. My X values, 0, subtraction from the formula, and -7. This is what I mean about keep, change, change, missing a minus sign. -3 plus 3 is 0. 0 plus 7 is 7. This is a horizontal line. It's got 0 slope. The 0 is on the top. If I did it the other way, said and decided that this is the first one and this is the second one, it really does not matter in the least. So -3 from the second one minus -3 from the first one, those are still my Y values. -7 minus 0. And now what do I get? I'm still getting keep, change, change. That still equals 0. Now it equals 0 over -7. Who cares? The rise is still 0. It's still a perfectly flat line. Doesn't change anything. So this is one of these formulas that you have to use if all you have are the points. Now I say that you have to use it, but if you have some graph paper, you don't necessarily have to do that. 3, 4, 5, 6, 7. So that first point is -7, -3. That's out here. The second point is 0, -3. Look at that. If you got graph paper, you're going to see right away that it's a flat line. It's horizontal. So you should know that the slope is 0. So when this handout here is showing you the rise and the run, excuse me, I got to pull that up. If it's showing you the rise and the run here, it's because there's a graph. If you don't have a graph and all you have are the values from the ordered pair, then you have to do the calculation. You could still graph it if you wanted to. It's totally up to you. And if you did all these problems on this first page, you'd see that the graphs give you one example of each type of slope, and so does the calculations. Here's negative slope in the first one, number 5. Woo. +2 for the second one, undefined for number 7, the third one, and 0 for the last one. So a different one example of each. Just watch those minus signs. In fact, that'd be a good thing to have on the checklist. If you got a problem or doing some calculations, go back and see if you have accounted for all the minus signs, all the negatives. Questions, anybody? So here's how we're going to end up using the slope stuff in geometry. A lot of times we're going to be more concerned with how a shape appears on a graph, or figuring out, proving that something is a particular type of shape. If you're familiar with what a parallelogram is, it looks like a rectangle that's been tilted over. Parallelograms have parallel sides. That's how it gets its name, parallelogram. So what would you guess goes in this first blank here? Parallel lines have the blank slope. Same, exactly. Parallel lines have to have the same slope. Otherwise, they're not parallel. By definition, they're going to cross at some point. So if I had two different lines put on a graph with the same slope, I would know that they're parallel. Now, the second definition here for perpendicular lines, two parts. Here's the clue right here. Negative parallel perpendicular lines have negative reciprocals. Well, what's a negative reciprocal? Do you remember what a reciprocal is? If you take any fraction and you flip it over, you have the reciprocal. And this is something that will come up over and over and over again. So if I have the fraction 3/4, what's the reciprocal?
4/3.
4/3. Right. And now to have a negative reciprocal, since this first term is positive, a negative reciprocal is going to have the opposite sign. That's what negative means in this case. It means the opposite sign. In fact, in algebra, a lot of times I will say that perpendicular lines have the opposite sign. They are the opposite sign and reciprocal slopes. To remember, it's two parts to the rule. Well, what about if I have the slope of -6? What's the reciprocal for that?
+6.
Nope. Remember, it's the flipped over version.
That would be 1/6.
Exactly. There you go. Good. And the positive part's right, because then if I take this negative and make a negative reciprocal, it becomes positive. And the reason I use this example of -6 as a whole number is because we can take any whole number, put it over 1, and make it look like a fraction. If you need a reciprocal, that's the best way to do it. See the fraction, see your whole number as a fraction over 1. Then all you got to do is flip it over and you got the reciprocal. So negative reciprocals would go into these, and it's just like what I just did. See, so if we've got 3/4 here, our negative reciprocal is going to be -4/3. Here's a whole number 2, so the negative reciprocal is going to be -1/2. What about number 3, -7/8? What's the negative reciprocal for that one?
8/7.
Yep, 8/7, it becomes positive. Now, these last two are kind of unique. 1 is the only number that is its own reciprocal, because 1/1 is the same as 1/1. 0 doesn't have a reciprocal, except in our case, for the opposite, for it to be perpendicular, what kind of line do we have to have? If we have a line with a 0 slope, we need another line to be perpendicular to it. What's the slope of that second line have to be? Let's go back to the whiteboard for that one, because you might need to visualize it. This is another one of those reasons why I constantly say, make yourself a drawing. So that line, I wanted it to have arrowheads. This line has a slope of 0. Remember the symbol for perpendicular looks like an upside down T. So what kind of line do we need to have to be perpendicular to that?
Parallel line.
Parallel is still going to have a slope of 0. I'm looking for perpendicular. I want it to look like this. I want it crossing at a 90-degree angle. That's why this symbol is made like that. It's a 90-degree angle. So what kind of line do I need to have to be perpendicular to this 0 slope line, to this flat line? You're throwing out some good ideas, Jonathan. I'm hoping somebody else will catch on here and start volunteering some ideas too.
Undefined line?
Undefined, yes, that's what I'm looking for. Because now this undefined line and I can draw as many of these on here as I want. As long as they're perfectly vertical. Yeah, not real good at that, but perfectly vertical. Every one of these vertical lines is going to be perpendicular to any horizontal line. Right? Because I don't care where you go, you got a 90-degree angle. Down here, you got another 90-degree angle. See 90 degrees here. Even 90 degrees to your XY coordinates, your XY lines. So that's kind of the oddball for perpendicular. And what you're going to see in these first few practice problems here okay, they're giving us problems that just have points. And the directions are use the slope to determine if lines A, B, and C, D are parallel, perpendicular, or neither. So if they're parallel, they're going to have the same slope. If they're perpendicular, they're going to have negative reciprocal or opposite sign and reciprocal slope. Neither just means that they have some other combination of numbers that doesn't match either of the rules. Because these definitions here are in fact rules that we can apply as long as we have graphs with XY coordinates, ordered pairs that generate lines for us. Those rules, you ought to put a star by them in your notes. You're going to come back to them again and again. And that's not just this lesson, it's future lessons as well. So use the slope to determine if lines A, B, and C, D are parallel. So here's the first pair. That's line AB. That's one line. And the second line is CD. How do you know if they're parallel? You can graph them, but you really need to do the calculations. And because they are ordered pairs, they're XY pairs, XY for A, XY combination for B, XY for C, XY for D. We can do the calculation. We can use that slope formula to find the slope. So for that first one, once you do the calculations, you discover that they both have a slope of 3/4. So they're going to be parallel. You will be expected to know how to do this calculation on this next unit test and probably in some of the practice problems. So let's try number 4 here. And I'm going to pause things again. So the rules are same slope or parallel.
It'd be perpendicular.
Are you sure? I got the same calculations that you did. Is this the negative reciprocal of that one?
No.
The sign is opposite, but the numbers are different. So these lines have no, they're neither perpendicular nor parallel. Okay, so if we had a parallel line, if we had parallel lines here with that both had a slope of -2/3, let's say that one looks like that. Well, this line here, our second line, almost flat. It's not parallel, it's not perpendicular. It doesn't follow the rules. That's why they have that kind of a problem on there to make you think about, okay, how do these rules apply here? And on these problems, and there's a lot of these problems in this section, that's what you have to do. You did the calculations, great, Jonathan. It's just that the interpretation of these rules as they apply to the calculation that you did, that's the trickiest part. Once you get used to doing a calculation, it's just numbers. Okay, now do your numbers match the rules or not? So you can see every one of these examples, 2 calculations. Example number 2's got a slope of 2/5, negative reciprocal, so they're perpendicular. Look at number 3, 14/7, -8 over -4. I've seen a lot of people look at problem number 3 and say those don't have any relationship. Well, you might think that if you didn't reduce them, but because both of these reduce to 2, right? Again, fractions, look at reducing them anytime you see fractions. Here's the one we just did, number 4. We got -2/3 on the first one and 1/4 for the second one, rise of 1/4, rise and run. So they don't have a relationship that's either parallel or perpendicular. It's just 2 lines on a graph. All those calculations are like that. So there's plenty on there to practice from. And the next section gets into the types of normal equations we have when we're talking about graphing. Anybody remember slope intercept? It's the most common one.
Is it y equals mx plus b?
Good, almost in unison. Very good. Y equals mx plus b. That's exactly right. That's the most common one. M, like I said before with the calculations, is always your slope. B is the y-intercept. Well, what's the y-intercept on these lines here? When you have the graph, it's easy. There's the y-intercept on number 2, whatever the ordered pair number is. It's always on the y-axis. Number 1 is down here. Ooh, number 3 is at 0, 0. That can make for a little tricky equation, because now you don't have a number where b goes. You're not going to write plus 0. And because you have the graph, it's easy to find the slope by doing the counting. Rise, let's see, number 4, rise 1, 2, 3, run to the right, 1, 2, 3. 3 over 3 is equal to 1, slope of 1. So my y-intercept here is 4. So that equation would be y equals x plus 4. So that's what all these problems on this page are like. When we start using slope intercept form to write equations, it's going to sound a lot like algebra. Questions, anybody? Okay, now the second type of equation form that we have with graphing, with XY graphing, is called standard form. I don't know who came up with that because it's not standard in the sense that it's used most often. Slope intercept is used more than any of the others. These first 4 examples that you see down here, 7, 8, 9, and 10, those are all in standard form. Anybody remember that the formal version of standard form? It's AX plus BY equals C. The problem with standard form is you don't know what the slope is and you don't know what the y-intercept is. So you have to do some equation solving to solve for M and to solve for B. And that's what's called a conversion process. You're going to convert them to slope intercept form. That's not a very good highlight there. Convert to slope intercept form by solving them for y. And that's just basic algebra, equation solving. Solve those for y. See, we have the third style. Now the rest is more about how you use that information is going to get even trickier now with this next section on comparing equations. Because now you're still using the definitions for parallel, perpendicular, or neither. But now you got to come up with the information in order to make that determination. So what are you going to look at? What do you need to know? There's one thing you have to identify to know if 2 lines are parallel, perpendicular, or neither. What are you going to be comparing? Now you got equations. What are you going to compare?
The x and y's?
Nah, only need one thing. What is it that determines whether lines are parallel or perpendicular? What were we just calculating?
The rise over run?
Yeah, all you care about is slope, right? That's all we did when we had the numbers. It's no different when you have the equations. So are these two equations in number one? Are those parallel, perpendicular, or neither? All you do is look at M. Slope is 5 for the first one. Slope is 5 for the second one. Those are parallel. Problem number 2. Slope is -3/2 on the first one. 2/3 on the second one. Those look like negative reciprocals to me, so those are perpendicular. Now you get down here into these others though, and they mix up the equation styles on you. That's where you're going to have to do some conversions. 3 and 4 are both in standard form. 7 is a mixture of standard form and slope intercept, and so on. So we're out of time for today, but what I would encourage you to do is to try some of these on your own. Maybe just take a photo and send it to me for feedback. You know, you don't have to do a whole page. If you're pretty confident and you just want to run with it, that's okay. But if you're not so confident and you need some feedback, that's probably the best way to do it. Just send something to me, text it to me, and I'll get back to you. Questions, anybody? All right, I'm gonna let everybody go. And I appreciate y'all being here today and for your participation. Be sure to go back in your stream and look at that one question that you're still not sure about. Send it to me. All right. See y'all Thursday.